because let's take a look at the entire breakdown here, right? So again, so far we finished all the way up to Unit 6, and we're starting Unit 6 today, all right? So again, I sent out a weekend update, but you guys know exactly what you're missing, okay? It's not a difficult process here. You know exactly what you're missing, so you need to make sure that you get that stuff done. But if you're on pace with us, you should be done with Unit 5, all the way up through Unit 5. Because today, tomorrow, this weekend, we'll work on complex numbers, which is Unit 6, and then we're done. Right, that's it. Unit 7 is our semester 2 exam. Then you are done with summer class, and you get to enjoy, the last couple weeks here of summer without having to worry about an online class here. All right, so again, I'm trying to motivate you extra, if you can't tell, to make sure that you get this done as soon as possible, because obviously the deadline is not this coming Friday, but next Friday, right? You have to finish everything by next Friday. So that's going to be the key here. All right, I want to take 30 seconds to just break down all of Unit 6 here. Okay, all of Unit 6 here. Unit 6 is the only one that is longer. Okay, of course it is, right? So the last one here, we've got to push a little bit extra, okay? Because we've got the introduction, and we're going to try to cover 2 of our lessons per usual, right? So 6.1 and 6.2. But this one here goes all the way up to 6.6, all right? So, we can try to cover our 2 lessons tomorrow. If we can get through it, we'll cover that 3rd one as well. But potentially you might have a little bit of weekend homework this time around where you have to finish 6.5 and 6.6. Okay, so you may have a little bit of homework here potentially this weekend, but that pretty much wraps it up for us. Okay, and we didn't have to skip any units. We got through all of the lessons, so you guys should really, take some pride in that, because this is a lot of work. But I just wanted to prepare you for this last little push here. Okay, so keep it up. All right. Going back to what we're going to cover today. So we're going to look at 6.1 and 6.2, which is talking about polar coordinates and graphs of polar functions. All right. So we're going to talk about that here. And that's all under this guise of Unit 6, which is talking about complex numbers. So if we look at the overview here, all right, it's talking about, or it's asking you first about have you ever considered how engineers and scientists develop or design even smaller, more efficient circuits to provide personal devices, right? Cell phones, computers, how can they make them smaller, faster, flatter, all of that things here, okay? And so one of these big design players is this thing called complex numbers. And I know we've dealt a little bit with it in Algebra 2 and in Semester 1 here, but we're really going to dive fully into this idea of complex numbers here, all right? And its different applications. So first off, we have to start with polar coordinates, okay? And polar coordinates are going to be similar but different to how we plot on our Cartesian XY plane. All right, so we'll highlight the differences there, but basically we're going to be dealing with coordinates, and instead of being X and Y, they're going to be R and theta. Right, so again, instead of being an X and Y point like we have on our X and on our XY Cartesian graph, we're going to have to deal with R and theta, where again R is radius, theta is angle, for our polar coordinates here. All right, so again, there's going to be some parallels and there's going to be some differences. So let's take a look at it here. All right. Earlier, we talked about, way earlier, we talked about the idea of number lines here, okay, and how we plot them on to correspond for a set value. Okay, then we moved on to plotting it on an X and a Y plane, right, and again, this is, of course, called our Cartesian plane or our XY coordinate plane, all right, and this here, of course, we expressed it always with our ordered pairs in terms of X, Y. So we would always put it in parentheses, X, comma, Y. And the reason we did this was because it denoted our horizontal and our vertical location. Our horizontal and our vertical location. All right. And this was called a rectangular coordinate system. All right, our rectangular coordinate system, because one, we're dealing in this terms of a rectangle, and we're also dealing in terms of horizontal and vertical displacement. So again, Cartesian plane, XY plane, coordinate system, right? All along those same lines here. Okay, but now we are going to look at shifting to this thing called a polar coordinate system, right? Or using our polar coordinates. All right, and it also, similar to our XY, it expresses the location of points and it uses ordered pairs. Right, so that's a similarity here. It expresses points and it uses ordered pairs. However, we're gonna find out that there are obviously a lot of differences here. So if we look at our polar coordinate plane here, all right, there are going to be, of course, some similarities. So if we look here, all right, this dot in the center is what's called the pole. All right, it's called a pole. So it's the center of the coordinate plane. All right, again, it was called an origin. Now we call it a pole, but it's a similar thing. All right, and the positive x-axis here is known as our polar axes. All right, our polar axes. All right, and again, of course, notice that our coordinates here are graphed with angles. All right, they're graphed with angles. And this specific example is measured with degrees here. Okay, and we talked a lot about this in the last couple of days when we were talking about especially vectors, right? We're talking about how we can express this length here as a coordinate, right? And previously we were calling it, you know, by the end point here, x comma y, right? We were calling it x comma y. However, another way of expressing what this distance is, or what this length looks like, right? We can write it in terms of its radius or its length, right? So we can call it our r value and our angle theta, right? We can call it our r value and our angle theta, all right? Where again, r is the magnitude of the distance from the pole, right? Our center point to the end point. Okay, or to the point on the graph, and they're calling it point P. All right, our angle theta is the angle from our polar axes to the line, right? So from our polar axes, which is our positive x-axis, to our line here. Okay, so we can measure that similar to the way that we did on our unit circle, right? So we're just now fully bringing it, we're bringing it home here. Okay, we're combining our coordinates with our unit circle, and now we're going to make our, of course, our polar graph here. Okay, and what we can notice here is that, of course, as before, you can measure the angles in either degrees or radians. Okay, so that's a good thing. You can measure it in either. You can go back and forth between, and we remember those conversion equations to get from degrees to radians or radians to degrees. All right. And I really like the way that they phrase this here. More formally, theta in polar coordinates is the angle bounded on one side by the polar axes and the other side by the line coincident with the line connecting point P with the pole. Okay, basically it's talking about using your reference angles, right? It's talking about using your reference angles essentially. Right, so this imaginary line here, okay, that connects our pole to our polar axes here. All right, and when r is greater than 0, so when r is a positive value here, our point lies on the terminal side of theta. All right, and what that means is it means it lies on the positive side. Okay, obviously our value is going to be positive. All right, when it's less than 0, it's going to be on the opposite side of the pole, right? So it's going to be on the opposite side of the pole. So this is our pole, right? This is our terminal side, our starting side, and this is our opposite side. So again, of course, when r is less than 0, there you go. Okay. So then looking at plotting these different points on our polar coordinates here. Okay, we have an example. So if a scientist is standing at the North Pole, they must find their way to a research station that monitors glacier ice thickness. The trouble is he only has the location written down in polar coordinates. He must use these polar coordinates to find the research station. Okay, so the research station is located at 500 feet and 120 degrees. So again, 500 feet is the radius. 120 degrees is obviously our angle here. Okay, so the first thing the scientist needs to do is use the angle 120 degrees to find the direction that he should be facing. Okay, so obviously you noticed he turned 120 degrees to face his correct direction. All right, now that he's got his direction going, he can then walk 500 feet to the research station. All right. So again, the most important thing, I think, or at least this one of the starting things, is obviously getting down that angle. Okay, so getting down that angle first. All right. Now, if we look here, this scenario could have been played out differently if the coordinates were negative 500, 120. Okay, so they're asking, how do you travel a negative distance? Well, it's not necessarily negative. Notice here, okay, notice you still have your angle of 120, but we've drawn now a dashed line all the way through that goes from our original angle through our pole and to our other quadrant of our graph here. Okay, so if we look, all right, again, it's still saying 120, but now if he was 120 positive, he would be walking this way in the positive direction. However, okay, he's walking negative, so he needs to just flip, right? He flips around. So he turns 120, turns all the way around, right? And he starts walking this way, all right? Walking this way. And I like the way they phrase this, backwards from the direction he faces when he turns 120. Okay, so it's not saying he's walking backwards. It's saying when he turns 120, whatever way his back is facing, that's the way that he's going to walk. Okay, so that's a good way of thinking about this here. All right, then obviously, of course, there's a couple reminders here that we need to go over. There's many ways to write polar coordinates for any particular point, right? There's multiple ways that we could write this here. Okay, we could have written our angles with radians instead of degrees. Okay, so that's saying the exact same thing there. All right, that's saying the exact same thing. We could have also written it, if we were on our unit circle here, we could have written it as multiples, right? So 2 pi over 3 versus 8 pi over 3. So indicating, did we go around once and then repeat, right? All of that kind of stuff, bringing back up our unit circle here. All right. And then finally here, we could have written it as our 5 pi over 3, right? 5 pi over 3 and still our negative 500 direction here. Okay, so a lot of different ways that you could have written this. And of course, that's the beauty of dealing with things in our unit circle-like fashion. Okay. So if we then decide to look a little bit more in depth at practicing some of these here. So if we plot the point 4, 225 degrees in polar coordinates. Okay, obviously we need to find out where 225 degrees is. And we can do that through a multiple of ways here. So let's take a look. Okay, so I thought they were going to explain it more, but then that. All right, well, first off here, what they could have done is they could have used this polar coordinates here, but notice here that all of these are in radians. Okay, so the first thing they should have done is they should have converted 225 to radians, right? Or used coordinates that we're talking about in degrees. Okay, but they converted 225 degrees into radians, all right, and it landed at this 5 pi over 4 radians, all right? Then what they've done is they've moved 4 units out. Okay, they've moved 4 units out. And if you notice here, this ring is 1, this ring is 2, this ring is 3, and this ring is 4. Okay, So they moved here, and then they moved, of course, again, 1, 2, 3, 4 dashed lines or rings out. Okay, so that's a way that we can solve this here. All right. For this one, we have 5 pi over 6. All right, so we're looking at 5 pi over 6. All right, and then it's saying -6. All right, so immediately your first thought is obviously to go here. All right, to look at 5 pi over 6. So we find our point 5 pi over 6. All right, but then we've got to notice -6. Right, then we've got to notice our -6. So we've got our angle. This is our immediate angle here. But since we're dealing with a negative value, we're going to be all the way down here, right? So again, it's like saying face 5 pi over 6, take the negative of it, right? And again, our negatives are down in this region here. Okay, now negative pi over 6. Okay, negative pi over 6. That would be 11 pi over 6. It's the same thing. So instead of going forward 11 pi over 6, we just went backwards by pi over 6 here. Okay, so that's our value, negative pi over 6. All right, now we've got a -6. All right, we've got a -6. So we're dealing with the opposite of it. All right, so again, we've got pi over 6, or I'm sorry, negative pi over 6, so we're facing this direction, and we need to go backwards 6 from it. So 1, 2, 3, 4, 5, 6, right? We go backwards 6. Okay, and obviously we can notice here that it's going to be similar points here because the two angles are because it's talking about the same point here, right? So it's talking about how there's multiple ways of writing the same coordinate, depending on if you want to use negatives or you want to use congruent angles, all of that kind of stuff here. All right, so there's lots of ways of writing this point, but this is a good way of breaking it down. So finding the degree first, and then moving out from there, or back from there. All right. So of course we've talked about the equivalence points, but here's a general rule here. So in general, if we have our point r theta, right, so our radius and our angle, then r theta plus 2n pi is going to be the same location, all right? And then obviously here, negative r of our angle, potentially plus or minus 2n plus 1 pi, is all going to be the same point. All right, so in other words, adding or subtracting multiples of 2 pi. All right, that's what it's asking you to do. All right, adding or subtracting multiples of 2 pi, right, just like we did with our unit circle here. All right, just like we did with our unit circle. Also, it's saying you can do this by also doing odd multiples of pi radians. So that's what this guy's saying here, right? So pi, 3 pi, 5 pi, right? Really offsetting it. So we've got that. This one's basically here talking about the reflection, right? So again, if we're dealing with quadrant 1, going off by 1 pi would put it in quadrant 3. If you're in quadrant 2, it would put it in quadrant 4. So talking about that reflection across the line there. That's really what it's saying here. All right. And of course, dealing with those coterminal angles from repeats of 2 pi, right? Going around the circle multiple times here. All right. So if we look for sets of points located at -2, 120, right? So -2, 120. All right. So one coterminal angle can be obtained by writing 120 plus 360 or 120 minus 360, right? So that's talking about going around the circle once or twice. All right. So again, this originally is 1. All right. This originally is 1. And so is if we go around once and still come there. All right. Another set of this could be if we're dealing with if we're dealing with the positive direction. So if we're dealing with the positive direction. So of course, if we take a second to really digest this, 120, our angle is right here. All right. -2 means we go backwards 2. Right. So even if we go around multiple times here and we start here, because of this -2 value, we're still going to go backwards 2. All right. Now, what the second part of this rule right here is saying, now we take negative of the R value. So we originally started with a -2, so now we're going to have a +2 here. All right, so this becomes +2, which means that now we're walking in the forward direction. So we need to make sure that our angle is correct. So we're down here at 300, right? Because that's what 120 plus 180 is, right? We go down to 300 and we're walking forward direction 2. All right, so again, that's another way of saying this here. All right, same thing with 5 -pi/4. All right, so we can deal with any multiples of -pi/4, right? Again, because they're going to do the same thing. They're going to go around and around and around, stop at the same point, go forward, round and round and round, forward. All right. Or the other thing we can do is look at if this value is -5, right? So -5, we would be having to walk backwards. So again, we'd be dealing with angles out here, because once we turn and face this angle, we're going to walk backwards 5. All right. And we can deal with multiples there. All right. So then I'll leave this to you, for you guys to practice here, but essentially with this, what it's asking you to do is add or subtract 2 pi, right? So add or subtract values of pi here. All right, so the way that you could check this would be adding 180 or subtracting 180. So if I click on these two, oh, apologies. So the original here, it's asking us to find multiples for this coordinate here. All right. So if we look though, okay, this point here is at about 225 degrees. All right. So without really being able to see what that value is, but it is 5pi/4 if you can read that. Okay. You can notice that since all of these values here, since all of these 6's are positive, that means we have to be facing the direction that we're going to eventually walk, right? So that means that we have to be facing whatever this angle is, all right? And so clearly it's not 45 because that would be up here. 130 would put us around here, and this is dealing with our 220 here, all right? And even negative values is fine, but -315, we start here, we go almost all the way around, right? So that doesn't make sense. So our coordinate here is 6,225. All right, 6,225. All right, and now we need to find multiples of that, right? So what this is then asking us to do here is again, use our rules. And since all of these have negative values here, all of these have negative values, that means we're going to be walking backwards. All right, so if we were able to see this dashed line all the way through, we would know that this 5pi/4 lines up with its reference angle of pi/4. All right, so we're going to deal with -6pi/4. All right, because again, we'd go to pi/4 and then we'd walk backwards here. All right, we'd walk backwards. Now, there's a lot of different options here, okay? So there's a lot of different options, and we can take a second to really walk through them here. But essentially, what you would do is just look on the coordinate. So -45 degrees puts me here, forward 6. Nope, that one's not correct. All right, so then we're dealing with positive values of 6. All right, so positive values of 6. So we're dealing here in this region. So 6 and 225. All right. And when we have this, okay, we could also, remember we said we can go around one whole time and then come back there. So an entire rotation is 360 degrees. So all we have to do is add 225 plus 360, and that gets us our value here of 6,585. Because again, it's just a multiple of 2 pi. right? It's just a multiple of 2 pi. All right. So we can see there that all of those points are correct answers that are equivalent to this original coordinate that we were given. Okay, to this original coordinate that we were given. All right, and this one here, I'll let you guys go through on your own. This is a really good practice problem for you. We're on page 6, so you guys can try this last one here on your own. All right. So then we have here this thing called coordinate conversion, okay? Coordinate conversion, and the definition that they give us for this here is the calculation of the coordinates for a point in a different coordinate system. For example, converting from a rectangular to a polar coordinate, right? So now we're gonna talk about, again, moving from our XY coordinates onto our polar coordinates. And yes, all of the work you did the last couple of days here is going to really help us do this, right? We're going to have to look at what is our values of R and what are our angles for these different coordinates here. So if we take a look at this video. Okay, we can notice, that we can turn an XY plane, okay? We can solve for this R value, right? We can solve for this hypotenuse. And we can figure out our angle here, all right? So we can figure this stuff out here and we can get it into polar coordinates here, all right? So some of the general rules here that we can use, or the relationships that we can use, is that R squared is equal to X squared plus Y squared. Yes, Pythagorean theorem here, all right? And we can figure out this angle by using our tangent function, our cosine function, or our sine function, right? Depending on what variables we have. If we have y and x, we would use tan. If we have x and r, we can use cosine. And if we have y and r, we can use sine, all right? And again, my general rule of thumb for this is if you're given an x and a y, use those. If you had to solve for your r, value, okay, then that's not correct. You had to solve for your R value, that is not correct. All right. So you can still use it, but again, you get into the issue of if you're rounding one answer and then you use it for another, then you're rounding that answer. So again, use what you're given there. All right. So of course then here, converting from polar to rectangular or rectangular to polar, right? We can use all of these relationships here. So just rewriting them to figure out what we're looking for. All right, so if we have our polar coordinates of R and theta, we're gonna use this to figure out our X, this to figure out our Y. And again, if we have our rectangular coordinates, like I said, you're gonna use what you have. So you'd have your X and your Y, so you'd use this relationship and you would use tangent here, okay? So then here, of course, we have some practice, all right? Again, using these relationships, using those relationships. So if we look here, all right? To convert this first point, we have 4,7 pi over 3. We need to get this into rectangular coordinates. All right, so we're dealing with polar to rectangular. So we're going to be using these two equations. So all we have to do is plug in or substitute our R and our theta into this equation. Okay, and again, when you do this, if you're going to plug it into your calculator, which is totally fine, right? You have to make sure that you're in radians here. Okay, you have to make sure that you're in radians. All right, so when you plug this in here, you should get an x equals 2. All right, same thing, you're going to plug it in, except now we're using our sine function to get our y value. And again, we get a 2 over square root of 3. All right. And then obviously we know our last step is to rewrite it as a XY coordinate, okay? And something, again, I need to point out to you here, all right, is that there is a difference between them asking you for an exact value and to calculate a value, right? Again, this is an example of an exact value, all right? 2 square root of 3, all right? So they're asking you for the exact value. Okay, because if I take my calculator here and plug in 2 square root of 3, that gives me a value of about 3.46. All right, but again, I had to round, So it's going to depend on what answer they want you to have for that, okay? And again, you can go back here and look at, okay, well, what is this angle give me on my unit circle, right? So what is sine of 7 pi over 3, right? You can do all of that stuff, okay? So again, we can calculate easily from there. Now, if we were to do the opposite here, we're going to follow these two rules. Okay, so use x squared plus y squared to give us our r value, and use our tangent function to give us our angle. Okay, so obviously here it's easy if it's 1 and 1. Okay, so 1 squared plus 1 squared equals 2. Then we're going to take the square root. So our r can be plus or minus our square root of 2. All right, and again, this is an example of where we don't know. It can be both values here. So we have to have them both. All right. Then for our tangent of theta, right, our tangent of theta, we have that equal to y over x, which is 1. Okay, so 1 over 1 gives us 1. And what we can say here is that two angles satisfy this tangent of theta equal to 1, right? So it can be pi over 4, or it can be 5 pi over 4. All right. And again, it has to be such that this is true, so it happens at 2 places, right? It happens at 2 places, all right? And what this is saying here is for whichever value of theta you use, you will need to select the correct value of r, okay? And what they mean by that is, if you look at this original point, it's in 1, 1, right? It's at point 1, 1. So that means our ending line on our polar coordinate has to be in the first quadrant, right? It has to be in the first quadrant because that's where the original point comes from, right? So what this is saying here is that you have to match up the correct r value with the correct angle value, right? Because if I have a positive here with my angle, right, this angle's in the first quadrant. So I would go up to my first quadrant, I would walk forward. But if I flipped this and had my negative r value with my first quadrant angle, I would face my first quadrant angle and then I would walk backwards. So I would end up in my third quadrant, right? And so that's not what we want. So we have to make sure that these are matched up correctly here, okay? And then you write them as ordered pairs. So we can write the positive here, or you could write the negative technically if you wanted to, right? But those are just congruent points there. All right. And I'll leave this practice for you guys here. All right. Again, the key is knowing if you're going from polar to rectangular, rectangular to polar, and utilizing these equations. All right, and then of course the last thing is making sure you're in the right calculator mode and knowing when to use your calculator and when to just use the exact values from your unit circle. Okay, so you guys can practice this as a good check for you. All right. Then there's one final thing we really need to talk about here, and it's called the special case of arctangent. All right, the special case of arctangent. All right, and remember, arctangent is the inverse function of tangent. It's also like saying tangent to the power of -1. All right, so to read this here, when converting from rectangular coordinates to polar coordinates, you must use the arctangent function, right? And we know that. We've got to use our inverse tan function in order to solve for our angle here. Okay, but since the range of arctangent is -pi/2 to pi/2, the only possible angles in the polar coordinate that you will get are in quadrants 1 and in quadrants 3, okay? So we will only get out answers in quadrants 1 and quadrants 3, okay? So because of this restriction here, points in quadrants 2, or I'm sorry, this was quadrants 1 and 4. I'm so sorry. I read that numeral wrong. Quadrants 1 and 4. So talking about the positive x value. Apologies. Sincerely apologize. So the quadrants 1 and quadrants 4. Okay, so what they're saying though is because we can only deal with the right half of the graph here, okay, points in quadrants 2 and 3 will always have a negative R value, right? Because we're always going to have to be facing quadrants 1 or 4, and to get to quadrants 2 or 3, we're going to have to walk backwards. We're going to have that negative R value, okay? So that's something that you just have to know. All right, and we can always, of course, find congruent angles and congruent points, but when you're doing arctangent function in your calculator, right, it's only going to give you out values for quadrant 1 and quadrant 4, so the right-hand side of the graph there. All right, and then finally, arctangent is missing points along the y-axis, especially when x is equal to 0, because that makes it not defined. Okay, so sometimes you might have to use an extended formula here. For example, if x is greater than 0, we use this formula here. All right, if x is less than 0 and y is greater than or equal to 0, right, you can add a pi to it. All right, if they're both less than 0, you subtract a pi from it. If x is equal to 0, you add a pi over 2. Or you subtract a pi over 2 depending on what the y coordinate does. All right, and what these little tricks will do is they will take the function from being undefined, right? It'll take it from being undefined to putting it into a region where we can actually calculate it and use it. All right, and all of this is fine mathematically because all we're doing is shifting the functions, and since we're shifting them evenly and we know that they are wave-like functions, right? They're very repetitive in their nature. This is an okay way to do this so that we can get the mathematical values to work out. Okay. So that's how we can come across those minor issues there. All right. So of course, then to wrap this kind of up here, okay, coordinate pairs. Coordinate pairs can be used to describe our XY system, or they can be used to describe our polar system. All right, and again, XY being the normal graph that we're used to, polar being being our new item here, where again, all we really see is we see our pole, which is that middle part, which was usually called the origin, and we have our positive x-axis, which is referred to as our polar axis here. Okay, and again, instead of having our xy coordinates, we now have our r comma theta, where r is our length of our line, or our magnitude, and theta is our angle here. All right, and we can have those angles in terms of pi's, in terms of degrees, radians, whatever. All right, and we talked a lot about how we can modify them, and we have congruent angles based on if we're facing forwards or backwards, or what our angle is. Are we going around multiple times? All of that kind of fun stuff. So really walking through those. And then finally, the last thing we talked about was mathematically going from a Cartesian plane, so that XY plane, to our polar plane. And again, that just has to deal with those quick couple of equations that we found out that relates our sine, cosine, and tangent function to our x, y, and r values, right? And then, of course, using our right-hand triangle rule of the Pythagorean theorem. All right, so really, really understanding that and trying that. And then, of course, those special cases where things might not work out perfectly, which is totally fine. We can just make a slight modification to our tangent equation depending on what our values of x and y are equal to. All right. So again, really, really knowing that if you get something for tangent that's undefined, right, all you have to do is then come here and go to the modified equation, all right, based on its restrictions. So of course, our checkup is going to deal with looking at those coordinates, converting between those coordinates, pointing them out, really plotting them, all of that stuff here, okay? So making sure that you can do both directions, so going from a point and actually plotting it, to listing out polar coordinates that could be used to give different lines, right? Understanding that it could be degrees, radians, you can have a positive R value, a negative R value, just understanding how that affects the movement on the graph. And then obviously our last couple of steps here are either given the coordinate points, given the polar coordinates, go to the rectangular, or given the rectangular, go to the polar. All right. And again, trying to pay attention to any special cases where tangent becomes undefined and using those rules we just discussed. All right. So of course, then, you have a quiz with this unit here. So you have got one quiz for 6.1. So hopefully not too terrible. And then we're going to go dive right in here to graphing these polar functions. Okay. So we've just looked at polar coordinates. Now we're going to look at something called a polar function, right? And what does that look like, and what does that generate? Okay. And typically when we're dealing with polar functions, they produce some pretty unexpected shapes. I think they're very pretty, but again, you can be the judge of that for yourself here. All right. Polar equations allow us to make equations in the rectangular coordinate system that are relations, right? So that are not functions, like conics, right? So if we were to plot a conic on our normal XY coordinate, it wouldn't be a function, right? However, if we switch to this polar coordinate here, this polar graph, it actually can become a function, right? And it can become a function, and we can plot it here. All right. So by using polar coordinates here, it allows us to exploit some unique functions and unique properties that can lead to really pretty graphs. Again, roses, spirals, a lot of different things that we're going to look at in here. Okay. So our polar equation here, as you can expect, is going to be R is equal to F of theta. All right. And again, that's saying R is equal to our function of theta. All right. And again, it's just the same way as Y is equal to F of X, right? So those can be replaced. Okay. So those can be replaced there. All right. And so if that's our equation here, we then have our graph as the set of these values, okay, of R comma theta. All right, that anything that works to satisfy this equation here. All right, so if we take a look at this graph here, okay, so we have R is equal to F of theta. All right, so again, R is a function of our angle. All right, so for these different angles here, it's going to give us different output values of R. So again, if you want to think about this as input and output values, our input value is our theta, our output value is our R value, okay? Those are our two values there, all right? And we can plug in different angles here, get out our different R values, and we can plot it. And of course, this one looks a little different than the graphs that we've used to seeing, all right? Of course, you can plug this into your graphing calculator, but before we can get to that, we've got to talk about how do you make these by hand, all right? And so the steps to doing that, of course, is to make a table of values, plot the points represented in the table, and then connect them with a smooth curve if it's appropriate, all right? So again, for this one here, we would just pick different values of theta, plug them in to this equation, get out our R values, make a table, plot it briefly on this graph, and try to connect it as best we can here. All right, so taking a look at what this actually looks like. If we've got our equation R equals 4 sine of theta, all right, we're going to create a table of values where theta, of course, is our input value or our independent variable, and R is our dependent variable or our output value. Okay, so if we look at our graph of 4 sine of theta, we can again do this multiple ways. So we can just plug it directly in, calculate out values. We can look at it as a graphical representation, since this is a function that we know, right? We know what sine of theta looks like. We can do a lot of different things. So let's take a look here. All right. So if we follow it along this line here, all we're doing is tracking up our different angles, right? Choosing some major points here. All right. And matching them up with the values of R, matching them up with their values of R. All right, you can even notice, obviously, they're going at points in between angles and at points in between R values. All right, but we can generate a table that looks something like that. Right? Then based on this, what we can do, since we have our table of values, we can try plotting the points on the polar axes here. All right, so what we can do then is show obviously the angle, and then the black dot represents where it is located. So 30 would be there, then 45 there, connect, right? And what we're noticing then is, though, when we get to certain values, right, we're facing this angle, but again, we're negative. We're negative. So we then reflect backwards. Okay? And if I look here at 2, -2, right, they end up being the same point for this graph here. All right? So if we look at this guy, all right, this is basically what our graph essentially did, was it went around, it went back around. All right, so what we can do then is we can sketch our graph, and again, we show it as a movement in the positive theta direction. All right, so again, start at our original value here, and we move in a positive theta direction. So it's saying move increasing angles. Okay, so if we sketch our graph, right, and we connect our points, it looks something along this line here. Okay, it looks something along this line here. Right? So, of course, I know this is what you all want to get to, graphing them on a graphing calculator. Okay, so our graphing calculators that we recommended, the 83 or the 84, will allow you to plot these on polar coordinates. Okay, so there are some steps we really need to discuss here. All right, the first one is you need to make sure that when you're in your mode, okay, you have to go down and make it into the mode where it says POL. Okay, so if you pull up your graphing calculator here, and let me stop sharing for a second. Let me see if I can pull up a window. So hopefully you guys have your graphing calculator handy. If not, let me try to pull up an image for you guys. Still trying, apologies. All right, so if we were to look at this screen here, okay, I know this isn't the same for everybody, but essentially here, this is what your screen of your graphing calculator looks like. If you hit that button mode, right, if you hit that button mode, all right, so it's to the right of the second button. If you hit the mode button, it pops up with a screen that looks something like this, right? If not identical. All right. So first thing, I think you probably should have noticed this. All right. You can express things in what's called normal numbers, scientific numbers, or engineering numbers. All right. And again, we use this scientific function in your chemistry classes here briefly. All right. Then the next important one for you guys is radians or degrees. And we've talked about that, right? Making sure you're in the right one when you're doing calculations. All right. And what this one here is talking about is changing it from being our normal function, right? Our XY function. We need to change it to this POL. All right. POL, which is standing for our polar graphs, right? We need to make that into our polar graphs there. All right, so it's saying change it to POL for polar mode, okay? We can also go radians to degrees if we need it, all right? And then we can enter, once we're in our polar mode here, once we're in our polar mode, we can go to our Y equals screen, all right? And what you're gonna notice though is that once you change it into your polar mode, okay, once you change it into polar mode, it no longer says Y equals. Okay, it no longer says y1 equals blank, y2 equals blank. It's changed, and it says r1 equals blank, r2 equals blank. All right, so it's even telling you, hey, you're in a new mode. This is how we express our equations here. All right, so again, it's kind of a nice reminder there. It's kind of a nice reminder. All right, and then the last thing you probably need to do is consider the window setting. All right, consider your window setting. All right, so what they're saying here is that for your window setting, usually you want to go and you want to set your window. Your minimum value, you usually want to set as 0, and your maximum value you want to set as 2 pi. All right, and you can actually type into your calculator 2 pi. All right. But of course, this is always dependent on what your graph looks like. So if you have a graph that's larger than this, you can always zoom out. You can always zoom in. You can move over left, right. But this is just a good general rule of thumb here. Okay. And then, of course, bear in mind that the normal shapes that you might be used to seeing on your graph might be a little bit distorted because we're now dealing with a different type of graph here. Okay. So that is a way of course, looking at your graphing calculator to solve these. Okay. Another one here is of course going back to just a polar graph paper, right? So I like that they gave you this printable one here, so you can always use this and reference this if you'd like, right? And personally, what I would do is I would have something like this, and I would keep it handy, and right next to all these degrees that are in radians, or sorry, these angles that are in radians, I would write the angles that are degrees that match up with it. So what is pi over 6? What is pi over 4? What is 7 pi over 6? Right? Mark this up here. Use this as your cheat sheet. Like, why not? Right? So then what we can do here is we can look at our different solutions to our problems. So that first one here is 4 cosine of 3 theta between 0 and 2 pi. Okay? So what we could do here in order to do this is what they were wanting us to do was use our new method of plotting by hand. So we would have to have made a table over here and a table of values, right? And they told us they only wanted to go us between 0 and 2 pi, okay? So we can go through and look at all of those different angles, right? We can plug them in, we can make our table, we can then sketch it by hand, all right? And then once we sketched it by hand, on our printable polar graph paper, we could have also looked at the solution using our graphing calculator. So if you plug this into your graphing calculator, 4 cosine of 3 theta, all right, 4 cosine of 3 theta, all right, it will give you out a graph that looks like this, all right, with this repeating pattern here, all right, it will give you a graph that looks like that, okay. If we look at this other one here, okay, it's not in our R equals format, right? So that's the first step here is we've got to put this in our R equals format. So this is going to be 7 divided by cosecant, or cosecant is also 1 over sine. So this is going to be 7 sine theta, right? It's going to be 7 sine theta. All right. And again, if we look at that, it's just this repeating pattern here. So R equals 7 sine theta, and there you go. It's going to go back and forth, back and forth, back and forth. All right. And then finally here, if R is equal to 1/2 theta with theta greater than 0. Okay, all that's going to look like there is it's going to look like our spiral here. It's going to look like our spiral here. All right. And again, you can test this out with some numbers that you know how to work with, right? And then you can plug it into your graphing calculator as long as your graphing calculator is in the correct mode, okay? And again, remembering our conversion formulas is going to be helpful for us when we're dealing with these different types of graphs here, okay? So one of the distinct advantages that they mention here that we have for polar coordinates is that we are allowed to, or I guess I shouldn't say allowed, we're able to express equations that are not normally functions in our XY coordinate systems. They become functions in our polar coordinate system, right? So that's a great advantage of using this polar coordinate system, all right? And again, it's really helpful with things that happen to be circles, ellipses, hyperbolas, spirals, right? We talked about flowers and rose petals and all of that stuff. Okay, so this is going to be really, really helpful for us when we're dealing with more non-perfect scenarios, and of course, going to be useful when you get into calculus here. All right. So again, here, if it says consider a circle of radius 5 in the rectangular coordinates, you know that the circle of the radius 5 is given by this equation here. All right. So we can then solve for our y function, our y value, and we can plot our lower and our upper hemispheres as a response to our two functions. All right. So again, if we needed to plot this on our xy coordinate here, we could just rewrite this in terms of our y function, right? We could just write this in terms of y. And of course, remembering when we take our square root, we have to consider the positive and the negative values, right? So this gives us a chance to draw that circle on our xy coordinate. All right. Now, the same circle of radius 5 in polar coordinates, right? It's still going by 5. It's going all the way around here. All right. And in polar coordinates, it seems that this circle is a function since for each angle, there is only one specified radius. Okay. So again, there's only one specified radius for each of these angles. Okay. So the polar equivalent of this function the polar equivalent of this expression is a function. Okay. So again, in our xy, it's not. In our polar coordinate, it is. All right. And again, for this one here, it's not a horizontal or a vertical line test, right? It's kind of this sweeping clock motion, right? So if you were to imagine that you are a hand of a clock, does it pass more than one point? And again, this one doesn't. All right. Then we can look at this thing called conics. I think you guys have talked about it. I'm hoping in geometry you talked about this. I'm almost positive you did. But you've got conics, right? And they're in this general form here. Again, you don't have to memorize this form, but just knowing that this is the form here, okay? And so E has to be greater than 0, right? Else this doesn't work here. And C is a constant, okay? And those two values here determine the shape of our conic. All right. So again, if we have E equals 0, then that's just a circle. Okay, that's just a circle here. But if we have other variables here for our conic, so if it's equal to 1, okay, our conic would be facing this way. If it's greater than 1, right, we have 2 facing outwards. And if it's less than 1, we have this kind of oval type shape here. All right. So again, very vastly different graphs. Vastly different graphs. All right. So of course here, more practice with converting from polar to rectangle. All right. So if we're given this polar coordinate of pi over 6, how do we get this in rectangular coordinates? Right, and we just plug in our values and we can solve, so we get these values here. All right, we get these values here. Okay, and then what we can do here is we can plug in and set the we can set these equations ending up equal to each other by doing some quick replacements with this common value of r, right? With this common value of r. So we can then set both of these equations equal to r, set them equal to each other, and then solve. And what we end up getting here is that y is equal to 1/3, 1 over square root of 3 of x. right? We can do that based on some simple algebraic expressions here, all right? So then, again, if we were using our graphing calculator, we could plot this graph and we would end up seeing that it's just a vertical line, right? It's just a vertical line, all right? And if we were to go to our rectangular coordinates, right, it shows it's not super surprising, all right, since this expression here reduces down to x equals -3, right? So again, there are some similarities there with that one, all right? And again, I'm gonna let you guys try these out, but again, it's based on just using everything we know and simplifying based on facts here. And again, if you get something wrong, it's going to tell you it's incorrect, and it's going to tell you why it's incorrect. Okay, it's going to tell you why it's incorrect. All right. So again, you can do these equations here and try them out, but essentially, again, what it's asking you to do is turn it into rectangular coordinates there. Okay, turn it into rectangular coordinates. Okay, so doing this, so on and so forth. All right. Again, similar concept here, rectangular to polar. All right, rectangular to polar. All right, but now we're dealing with something that maybe doesn't look as nice. So we've got an x minus 2 quantity squared plus y squared equals 4. Right? So now we have to turn not just a specific point, but the entire equation into a polar coordinate form here. All right. So what we do for that is obviously we just replace our x and our y. Right? We replace our x and our y with what we know that they're equal to, so that r cosine or that r sine, and then we follow out algebraically. All right, so again, we have to square both of the values for y, so this turns into r squared sine squared theta. All right, and then for this one here, if we wanted to carry this out, which we do, right, we end up having to FOIL out these two terms, combine like terms, and then simplify here. All right, and once we've got this simplified here, we can then put it in terms of our r value, right? We can put it in terms of our r value by moving that 4r cosine theta to the other side, dividing an r from both, we end up with this equation here. All right, so then once we've rewritten it, we can clearly see our graph on our polar coordinate here. All right, same thing with a hyperbola. Okay, same thing with a hyperbola. We just replace our x and our y values with what we know they are from our conversion, and then we simplify. So replace, simplify, put it in terms of r. Okay, and of course we can always check by plotting our graphs here. We can always check by plotting our graphs. All right, so again, practice problems for you guys to try that out here and seeing which one is accurate. All right, and as everything, right, with graphing, it's easier if we can kind of chunk them together. So one of these kind of chunks is a family called roses. All right, roses. And so with roses here, they have this type of equation here. All right, and then if we plug all 4 of these in, we're going to notice a lot of similar things here. All right, so if we plug in with our 2, our value of 2, we get out this thing that looks like it has 4 petals. If we have 3 sine of 3, okay, we end up with 3 petals. 3 sine of 4, we end up with 8 petals. And 3 sine of 5, we end up with 5 petals. Okay, and they'll talk about this here, but what you should notice is there's a pattern with our odd values and there's a pattern with our even values. And hopefully what you picked up is that with our odd values, it's whatever number of theta it is, right? So if it was 3 theta, it was just 3 petals. If it's 5 theta, it's 5 petals. With the even numbers, it is the number times by 2. So it wasn't 2 petals at the beginning, it was 2 times 2. So it was that 4 petal. right? When we had 4 theta, we actually had 8 petals, okay? So again, you can plug this in your graphing calculator to make sure you're getting this out here, but that's what it will look like. All right. So again, it's called the rose. And again, can you imagine why? Yes, because it makes petals, right? So it makes the petals. And of course, we just talked about what that does and why it does it. And in general, for a sine of n theta, okay, the graph is going to be a rose. Same thing with cosine theta. The graph is going to be a rose. All right. For even values of n, in both cosine and sine, the rose has 2 times n petals, right? So whatever number is multiplied by theta, it's 2 times that. All right. The odd values have the n number of petals. So whatever the odd value is, that's how many petals it has for both cosine and sine. All right. And then finally, the constant A, so that constant out in front, whether it's a 3, a 5, a 1, that determines the length of the petals. So how far out each of those petals are going to go. All right. And that's really what the summarizing of rose curves. Okay. So identifying those major features here. All right. Now there's this one called cardioids. Okay. Cardioids. And they're really useful here in microphones. Okay, they're really useful for things in microphones. So again, dealing with 0 and 2 pi, we have these 4 equations here, and hopefully you can notice some similarities. So if we look here, it kind of looks like a heart shape, like a sideways heart shape. All right. Same thing with this one, sideways heart shape. Sideways heart shape, or upside down heart shape, upside down heart shape. All right. And what I need you to notice here, with my sine functions, I'm dealing with my heart facing up or facing down. Okay, I'm facing my heart facing up or facing down. All right. With my cosine function, I'm dealing with my heart facing left or facing right. Okay. But notice with all of them, the little bump on the heart always occurs at our origin. Or I'm sorry, I should say our pole, our previously known as origin. Okay. So that's going to be something to notice here. All right. And hopefully what you can notice is the difference between the positive and the negatives. All right. The positive and the negative. So if it's positive, it's open to the right. If it's negative, it's open to the left. If it's positive, it's open down, open, up. All right. And of course, it's called cardioid because, like, cardiology, dealing with your heart, right, makes a heart shape. But Ching, hopefully that's familiar to you. Okay. So this family of curves is described as cardioids, okay, because it's heart and shape, cardioids. All right. In general, it has the form of A plus or minus a cosine or sine of theta. Again, A is greater than 0. All right. And the length of the cardioid is 2A. It's 2 times A. All right. And something you need to notice is that if I go back here, notice it was the same value. It's 3 and 3, 2 and 2, 3 and 3, 3 and 3, right? It's got to be that same value. So that A value is consistent in this equation here. All right. And again, 2 times by A, 2 times that constant is the length of the cardioid. All right. And so an interesting way of thinking about this here is if the cardioid is the curve traced out by a fixed point on a circle when it rolls around another circle of the same radius. Okay, I don't know how that would help me remember this, but I think it's kind of funny. All right. So again, it could help you out to remember that it involves the same constant, right? It's got to have that constant there and that constant there. All right. Then we can look here at I've always called them limacones, but let's see how they pronounce it here.
Use the graph paper and your graphing calculator to test your ability to graph these equations.
Oh, apologies.
Families of polar graphs. Limasones.
Okay, so they call it limasones. I've always called it limacones, sorry. So limasones, all right. So this is another type of equation here, all right. And if we look at this, all right, we'll notice some differences here, all right. It looks sort of like it wants to try to make a heart, but it doesn't fully, right? It still has that tiny little bump there, looking kind of like our heart, but it is not touch the pole there. All right. And again, what you can notice here is that cosine is opening to the left and the right. Sine is going to open up and down. All right. Again, same thing. If it's negative out in front, it's opening this way, versus if it's negative cosine, it's going to open that way, right? So there are a lot of similarities between our limasones and our cardioids. All right. So looking at this here, we obviously noticed that we had two different constants, okay? We had two different constants. And we have to note that A needs to be greater than B, all right? A needs to be greater than B, all right? A needs to be greater than B in order to do this, all right? But what happens if B is greater than A? If B is greater than A, it goes beyond the cardioid, right? It goes beyond the cardioid and actually makes a loop in the middle. All right, it goes beyond our cardioid and makes a loop right in the middle. All right, so if A is greater than B, it makes a kind of flattened out heart. If B is greater than A, it makes this little twist in the middle here. Okay, again, still opening the same directions depending on if it's negative or positive and if it's sine or cosine. All right, so then if we look at this one here, let's figure out how to pronounce this one, since apparently I've been pronouncing that one wrong for a while.
Families of polar graphs. Lemniscates.
Okay, so lemniscates.
The last.
All right, our lemniscates here. They involve an r squared term. Okay, so therefore, when it involves an r squared term, we know that if we were to go to our graphing calculator, we'd have to take the square root of both sides here in order to plug this in. So technically, when we plug this into our calculator, this isn't r squared equals 4 cosine of 2 theta. This is the square root of 4 cosine 2 theta. All right. So if we look at these functions here, all right, it looks like this shape. All right. So we have 4 cosine and we have 4 sine. All right, and so notice here, they have the same inside of 2 theta, but the difference being here is that they're sine or cosine. So cosine is on our axes here, and sine is off axes, right? It's off axes. This looks like a 45-degree angle here. Now, if we look at our larger value, okay, you can obviously notice it's going to have the same behavior. It's just going to change how far out, right? So the radius of our graph here. All right. So this is derived from the word pendant ribbon. Okay, I guess it looks like a ribbon there, right? And this is what it's saying. You've got a squared sine and a squared cosine. All right, a's got to be a positive, and it's going to give you that ribbon-like shape. All right, give you that ribbon-like shape. And then finally, we can talk about the symmetry tests for polar graphs. Okay, sorry, hold on. Okay, so we did a lot of work in previous units talking about our rectangular functions as being symmetric, about this, about that, x-axis, y-axis, no symmetry, are they even, are they odd, right? All of that fun stuff. All right, but you should have been able to notice, right? I think I mentioned it a few times, that a lot of these polar graphs have symmetry, okay? And the way that we can describe symmetry is going to be similar to how we describe it with the rectangular graph here. all right, except for when we describe polar graphs as having symmetry, we talk about it being across the polar axes, okay? The polar axes, which is obviously the positive x-axis here. We talk about it having symmetry across our y-axes, okay, so our up and down. We talk about having symmetry about the pole, so that origin point there, or we talk about it having no symmetry at all, all right? And there are tests for the 3 types of symmetries, okay? And so what we can do then is, obviously we could look at it and make these conclusions, but mathematically, if we wanted to check values, if we wanted to look at symmetry about the pole, right, we can substitute in, instead of our r comma theta, right, we can substitute in these different values, right? So if we substitute in these values and we get the same point, right, we would have symmetry across the pole. If we have about the line y equals pi over 2, that's our 45, or I'm sorry, that's our 90-degree angle, right? That's our y-axis, our pi over 2. Okay, so we would plug in a negative r value, negative theta, or we would plug in pi and theta minus, I'm sorry, r and pi minus theta. All right, and then finally about our polar axes, that's where, of course, we're equal to 0. So that would be having a negative theta or a negative r and a pi minus theta. All right, so trying to get over here and seeing if it's the same point there. All right, so we can test those and substitute those guys in. All right, so if we look here at our function of r equals 5 cosine 3 theta, it's asking us to determine a type of symmetry, if any, visually. Do we have any visual symmetry? All right, and I'm gonna go with, if you look at this, it looks like it's got a pattern here. All right, so 1, it looks like there's a repeating pattern. All right, and if you look at this here, you've got to ask yourself, well, is it reflected across this? No, there's no symmetry. All right, is it look to be across the origin or the pole here? No, but it does look to have some relationship here to our polar axes, as this right here is on our polar axes. All right, so if we look at our symmetry here, if we were to draw this right here, look, we have the symmetry. Okay, we have symmetry across that polar axis. It's split in half, so that's symmetric. This is symmetric with this. This is symmetric with this, right? And then what we can do here is we can replace our values and rewrite them. So instead of having r theta, we can have r negative theta or negative r pi minus theta. And why does this work here? Because here, the test is saying that we should get the same r value at angle theta and at angle negative theta, right? That's what this first one is saying here. So at angle theta, we should have the same value as at angle negative theta, which we end up having, right? And the other one, pi minus theta, right? So we would have the same angle there, right? We would have the same angles there. So that would be saying pi minus theta. That would put us here. All right, and reflecting across that would put us also there. Okay, so since those two are symmetric here, those two are symmetric there, this is telling us that this is a symmetric graph about our polar axes. Okay, again, testing it algebraically, we can simply then go in here and apply our test, right? We apply our test, so we change it from positive sign to negative, or sorry, positive theta to negative theta here, and we plug it all out, and when we do that, we end up with the same expression here. We end up with the same expression because, again, remember, cosine, when it has negative values, it's going to end up with the same output. Okay? So again, to graph a function with a polar axis symmetry, you only have to graph it from 0 to pi. Okay, so you graph from 0 to pi, and then we reflect it across the axes. So that's what it's showing you here. If we know ahead of time that it is reflecting across the pole, or if it's symmetric about the pole, we only plot here, and then we just flip it. So it's a pretty simple process here. All right, if we look at this graph here, okay, it's asking us what is it symmetric, and it's symmetric about the pole. Okay, the reason that is it's not reflected directly across the y-axis, and it's not symmetric about our polar axes. So if it's going to have symmetry at all, it's got to be about this center point here. All right. So we can see our symmetry by pulling a couple points here and looking and noticing that, of course, they're going to match up here. All right. Algebraically, it's asking you which test do you use and why, right? And I'm just, oh, I was hoping it would just give me the answers right off the bat. All right. But again, this would be using your study sheet here. I don't expect you to know these off the top of your head. Okay, using your study sheet here, you can test for the symmetry here. All right. But let's take a second and digest. If I didn't have my study sheet, how would I know that these are correct here? How would I know that these are correct? Well, what this is saying here is that if I have r theta, okay, if I have r theta, all right, yes, going around again and having r theta, it should match up, right? That makes sense here, all right? But it should also match up if we have our angle plus pi, right? So we go pi plus our angle, right? Our angle plus pi. So what it's saying is going halfway around the circle and adding on to our original equation there. Okay. And I do believe, if I'm not mistaken, this should be a negative r value as well. Okay, this should be negative r comma theta. And the reason that is because, of course, we go theta here and we walk backwards. So that's not a correct equation there from them. All right, but again, if we look here, we can replace either of these. Okay, we can replace either of these. And again, all it's doing here is it allows you to look and match up those different points there. All right, we can algebraically do this and we can apply our test. And when we're graphing this function, if we know that it's symmetric about the pole, we can just graph this first quadrant here, and then we can reflect it across into our third quadrant down here. Right, we can reflect it across our origin or across our pole. All right, and then finally this cardioid here. It is an example of symmetric across our y-axis or our pi over 2 axes. Okay, we can use our test here. We can look at our symmetry and basically realize that we have points that reflect across this. Okay, so we can look at that here. All right. So again, to finish it up, I know this was a lot of information, but hopefully you were able to pick up on some patterns there. Okay, and really a lot of it has to do with truly understanding that first unit that we came across. Okay, first truly understanding that unit 6.1, it really helps with this, because again, all we're doing now is, now that we understand the coordinates and where they're located and how to locate them, right, we're actually dealing with plotting them. So again, to plot them by hand, you could make a table of values, plot the points, and then connect them. And we talked about doing that. So you can sketch that out on your graph here. But then we talked about converting from polar to Cartesian and Cartesian to polar or rectangular, right? And again, all that is doing is simply replacing the values and then solving any algebraic issues that there might be in order to put them in the correct form, okay? So in order to put them in the correct form. All right, and then we talked about some specific cases here. You know, these are talking about conversions, but we talked about some specific cases here of roses, what happens with roses, cardioids, which look like a heart, our limacons, or limus, whatever, however they pronounced it, that I've been pronouncing it incorrectly. All right, and then our limnoscates. All right, so those are kind of the three that we talked about here. All right. And then we really highlighted our different types of symmetry. So again, we have symmetry about the pole, which is our positive x-axis. We have symmetry about our line of pi over 2 or our y-axis. And then we have about our polar axes, which is that 0, 0 point, right? That 0, 0 point. Oh, I'm sorry, I lied to you. I flipped polar axes and pole. Our pole being obviously our 0, 0, and our polar axes being basically our x-axis. All right. So there's that one here, and 30 more seconds we'll finish this up. So obviously with your checkup, you're gonna have a lot of these problems here. And again, making sure that you can do these in all ways, shapes, and forms, okay? So dealing with writing the different points, right? So right here, it's telling you write the scale you're using, identify the graph, and state the symmetries. Okay, so what does this actually look like? If r equals 6, what does that look like? Same thing, if it equals just pi over 3, what about an actual equation? All right, and for you guys, the easiest way is to look at the equation, figure out if it matches up with one of those specific equations that we talked about, right? And seeing if you can figure out some of the values. Obviously, you can always plug it into your graphing calculator, but it's going to be very hard for you to actually plot these points specifically if you can't figure out some of the major points or the major characteristics that these graphs are going to have. All right, and it doesn't just deal with the graphs here. We also have to talk about how to transform equations fully from the rectangular to the polar, or vice versa, right? So making sure we can do that, talking, and then finally putting it all together here with our different equations. All right. So again, that kind of wraps up what we're doing in class today. So again, just a reminder, we introduced our unit 6, which is on complex numbers, and really that's putting it together here, starting with polar coordinates, right? So going from our XY graph to now our graph that deals with angles and radiuses, and then not just looking at specific coordinates, but actually making polar functions into graphs. We talked about specific types of graphs. We talked about different types of functions, okay? So that's kind of what you have to cover today. Like I said, tomorrow we'll cover at least these two, and then potentially for the weekend, you'll have the last two to finish up here. Okay, so again, please make sure that you're working super hard so that you don't have a lot of work next week. If you need anything from me, guys, let me know. Otherwise, I will just see you tomorrow, and keep working hard. Goodbye.